Hello, in this video I'm going to try and clear up any potential confusion that might arise when thinking about Newton's law of universal gravitation and the local acceleration due to gravity. So this is the statement of Newton's law that we looked at in the previous video, and then g, little g, this accelerator is 9.81 meters per second squared, this acceleration due to gravity that we use throughout classical mechanics. And sometimes people are thinking, well, why have we got two descriptions of gravity? So I just want to show in here that actually it's the same description. So we don't want to get any confusion creeping in over this. Now let's pick apart different bits that we've got here. So Newton's law, the universal gravitation, is the force due to gravity exerted by two objects on each other is the universal gravitational constant multiplied by the masses of the two objects, so little m and big M, divided by the square of the separation of the two objects. So force due to gravity increases as the masses increase, and it decreases as the separation increases. So that all makes sense. So we're happy with that. Now, if we then think of what's happening with the Earth, because that's what we're considering when we're doing all of our classical mechanics problems at pre-university level anyway, and aside from little forays that we do into astronomy and astrophysics and such like, we're thinking about objects that are either on or near the surface of the Earth. So what is this actually meaning? Well, the radius here, the separation between our two masses is going to be the radius of the Earth. So if we've got some object, there's the surface of the Earth, we've got some object sitting on it, our separation, the r in here, is going to be the radius of the Earth. And the radius of the Earth is around about 6,370 kilometers. That's pretty big. You think of the sort of problems that we're dealing with in classical mechanics at the moment. I mean, this object might go, I don't know, 50 meters up in the air. That would be quite a lot, even if it was 100 meters up in the air. We're not changing much here. If we're saying that our R has gone from 6,370 kilometers to 6,370.1 kilometers, well, it's not much of a big deal, is it really? So our R isn't changing much. Our masses aren't changing. Big G is just a constant anyway. So really we're saying that there's not much going on here. There's not any change really in the force due to gravity. So we're then treating this force as being constant over the small changes in separation that we're considering in our problems. So another way of thinking of that is if you really zoom out on the Earth and make it that size, and we were going to draw the gravitational field lines. So say we were going to draw in a radial field, and it's a radial field because our force, which is the concentration of field lines at a particular distance, is inversely proportional to the square of the separation. So it's changing because we've got a length squared here. It's going to be something to do with an area. So if you think of this being a sphere, we've got how is the area of this sphere changing as it's moving out. So these field lines are dropping in that squared fashion because it's an area that's extending out away from the surface of the Earth. So we've got to try and think of this as being the surface of a sphere. I know I'm drawing it on a flat plane here, so it looks like we've just got a sort of a flat surface rather than the surface of a sphere. But if you imagine a sphere going round here, all of these field lines are moving out with the area of the surface of this sphere. So it's dropping by an area here. But very close to the surface. I mean, if we've barely moved, which we have when we're looking at these problems, if we've only moved by 100 meters or so, these field lines are more or less parallel. If we were going to draw all of these gravitational field lines on, for a very small change in separation, we can make these field lines parallel. And instead of looking at a radial field, we're looking at a uniform field. So we're just making that approximation for stuff that goes on the surface of the Earth, where changes in separation are small compared to the actual radius of the Earth. We're going to approximate our gravitational field as being uniform, as in F isn't changing. It just stays the same because R is barely changing. What that then means is we can just plug in numbers into this formula and just simplify it. So we're going to compare our G(m)m) over R squared and Newton's second law, F equals ma. Now, we want to get what this A is, because this is going to be constant. We've said that F is constant because we're making it a uniform field. The mass isn't changing. So if these two things are constant, A is going to be a constant. And this is what we're calling our acceleration due to gravity, little g. And that little g is equal to this without the m in it, because that m is that m. So the G(m) over R squared is our acceleration, is our little g. So our local acceleration due to gravity is capital G, capital M over R squared. So we're just plugging in values. We know what our capital G is. G is 6.67 times 10 to the minus 11. Trying to remember the units. It's meters cubed per kilogram per second squared. So that's our G. Our mass of the Earth is 5.97 times 10 to the 24 kilograms. Our radius of the Earth, I've already said, is this. That's our R. If you put those numbers in to here, this right-hand side, then you get G is equal to 9.81 meters per second squared, which is what we use all the time in our classical mechanics problems and analysis. So this is just one theory. There aren't two things going on here. We haven't just suddenly, magicked up this idea of little g, our acceleration due to gravity, and ignored Newton's law of universal gravitation. They're the same thing. It just means we don't have to continually type into our calculators big G, the mass of the Earth, and the radius of the Earth. We're just doing that bit in advance because we can just keep on reusing this 9.81 over and over and over again. So it is all one theory and it is all unified. We're just saving ourselves a load of time by making a little approximation, saying, well, approximately the field is uniform rather than radial over small changes in distance. And then we can use this 9.81 everywhere, and we're still going to get accurate results. So hopefully that clears up any potential misunderstanding there might be in this idea that we've got two completely different treatments of gravity. We haven't. It's the same treatment. We will get a different treatment of it when we move to general relativity, but we're not doing that in classical mechanics. In classical mechanics, we're all unified on this one theory.